Okay, we are recording, so if others then want to see the video, they can. So the point is, we proposed you, and you have it in the shared directory, a sort of exercise to be done. And let's say the key point of this exercise is you have these various types of facades that each of you is developing in their projects. And what we suggest you to do is to calculate the features of your present stratigraphy and compare them with the best possible stratigraphy from the energy point of view. Then you might have other criteria for choosing. So here, this, and to do this comparison, one step is to calculate the thermal and hygro properties of your the stratigraphy that you have developed till now, if you have one. So this tool is a, you have the address into the PDF we sent you. The best way to use it is to create an account, which is free of charge, which allows then you to have a folder where you can save your work for further. So then I've taken, and now we are considering walls. So I took an example of a wall and I modified it a bit to do the exercise now. So here you find examples of many different structures for roof, floor, basement, ceiling, basement ceiling. So you can play a bit if you want examples, but I just took an example of a wall, and the wall is described here. The layers are numbered and ordered from inside. Inside you have air. The first layer, let's say sort of layer, the first element is indoor air, which is set here for, we are considering a winter situation, or let's say here the conditions are for winter, so there is inside 20 degrees Celsius and 50% humidity, and outside you have outside air at -5 degrees Celsius and 80% humidity. So we imagine a winter, relatively cold, relatively humid outside condition. So the structure, so 1 is inside and 6 is outside. It's often, that's the numbering in the calculations from indoor to outdoor. You have a layer of plaster, layer number 1. Then you have bricks. And here we have 24 centimeters, so bricks, thick, 24 centimeter. So it's a solid wall with a certain mass, as the ones, for example, that the African team is using. So a solid part, relatively thick. It might be even thicker, depending on, obviously. So we are considering an opaque wall. We're not considering the window here. We're just considering the opaque part. So then going towards outside, oops, what happened here? Mi ha tolto via il... ok. Okay, then there is a plaster to finish the bricks and have the possibility then to apply insulation. I guess now I don't want to have insulation. We will see the effect. So here it's very useful, this tool, because it's very quick to change the stratigraphy. You can take a layer and move it up and down. And you can turn on or turn off a layer. So for example, here, let's start with no insulation. So we have just the bricks, plaster inside, plaster outside. Down here, you see a summary of the properties. So you have a U value, a transmittance, thermal transmittance in watt per square meter Kelvin of 2 and something. So this is the feature that allows you to calculate the flow of energy from indoor to outdoor, transmittance per area, per delta of temperature, tells you how many watt are per square meter, per area, so how many watt are leaving the building through the structure in stationary conditions. Here we are discussing a situation where indoor temperature and outdoor temperature are constant for many hours, let's say a couple of days. So we are in a situation where everything is constant. The temperatures and the temperature distribution within the wall is constant. So under these conditions, the software does simple calculations and shows you directly the result. So down here, it tells you the U value, which is quite high, and the fact that there is condensate. So in this situation, as depicted by these drops of water here, the software tells you, oh, wait a moment, water vapor will condensate to liquid within the wall and in the long run will damage the wall. Besides the fact that it changes its conductivity and makes it more conductive. So you have here a summary, and we will see, and also correctly, Roberto was highlighting, let's look here, interior surface temperature is 9.6 degrees Celsius, less than 10 degree. So the surface of the wall will be rather cold. And comfort is due, as we discussed in the previous lectures, to air temperature and to the mean radiant temperature, so the mean temperature of the surfaces. And here you have a surface which is relatively cold. It's not at 20 degrees, it's at less than 10. Then, this is the summary. Then you have various sections where it tells you the U value, okay, the calculation that we have shown, and some other informations, temperature of the inside surface, temperature of the outside surface, and so on, and a description of what's the temperature in the various points of the structure, in the various layers. Moisture tells you where condensation occurs, and this blue area is the area where there is liquid water, and this happens within the bricks. So this is definitely a huge problem. If you know about So relative humidity is this line here. You see that this line goes to 100% relative humidity. So condensation. 100% relative humidity means you have liquid present. So it tells you in both ways, with the color and with this line, the relative humidity goes up into the structure, and in the bricks, it's 100%. And then we have the heat section, which tells you what is the behavior under warm conditions outside. This is no more a stationary calculation. Here, the assumption is the outdoor temperature is this red line. The outdoor temperature goes up to 32 degrees Celsius at 4 o'clock in the afternoon, and that goes down to 18 during the night. So we have a very big temperature shift between day and night. And the software, so we are not in, the temperature is not constant. For winter, the software does a calculation with constant temperature, 20 degrees inside, -5 outside, let's say for 2 days. For summer, it never happens that the temperature is constant in summer. You have high temperature during the day, low temperature during the night. So the calculation is done with this variable outdoor temperature. And here the software calculates what happens to the indoor air temperature. The blue line is the indoor air temperature. And you see that if at noon it's 23, it goes up late in the evening because the heat coming from outdoor crosses the wall and it takes time, and then it gets to the interior. So you have a wave of heat traveling from the outdoor surface to the indoor surface, and it takes the phase shift, which is between the maximum outdoor temperature and the maximum indoor temperature. There is a phase shift of 8.7 hours. So the heat coming from outside takes 8 hours to get inside, going through the opaque wall. Obviously, if this heat enters other ways, because you open a window, then it's a different thing. Here is how the heat travels through the wall. And it takes 9 hours to go from outside to inside, the heat wave, the maximum. So now let's try to see if we have 2 problems. No, we have 3 problems. The transmittance is very high. This U value of 2 watts per square meter Kelvin is very high. There is a lot of energy going away from your building to outside during winter. First problem. Second problem, the interior, the surface of the wall is quite low, so this will be very uncomfortable. Third problem, you have water vapor becoming liquid water inside the wall and damaging the wall. And the fourth problem is that heat is coming in summer, and the phase shift is not very big. We would prefer to have the energy coming in at 4 o'clock in the night, because then if I open a window, I get in the external air at 18 degrees, and I wash away this wave which is coming through the opaque wall. So the heat is coming in through the wall. I open the window and I let this energy go out. If this wave comes when external air is cold. If it comes too early and the external air is still at high temperature, I cannot wash away the energy. So the best for summer is to slow down the wave coming in so that it comes in when the outdoor air is very low. I open the window and I let it go out. So to achieve this, it's quite simple because we can turn on the insulation, the external insulation. Let's start with 5 centimeters of insulation. I just changed the thickness. So now there is an outdoor insulation, outside insulation, and things are going definitely already better. The U value has gone down from 2 to 0.6, which is, we have divided by 4 the transmittance, so the loss of energy from indoor to outdoor in winter. The temperature of the surface, of the interior surface, now it's 16.5. It's no more 10 degrees, it's almost 17. So we have raised the temperature of the indoor surface. And there is no more blue things here. So apparently from this, you see here, condensate 0 kilograms per square meter. So it says there is no condensate, no water, no liquid water. And we can check this in more detail in the moisture window. And here we see that the relative humidity, this blue line, this time is never at 100%. It's at 60, 40, 80%. So the black line, which is the relative humidity in each point of the wall, is never 100%. So there is no condensation, because condensation is at this saturation point, which is 100% relative humidity. Why there is no condensation? Because the temperature of the bricks now is higher than in the previous case. We had condensation in the bricks because the bricks were cold. Now, having an external layer, like my jacket, the bricks remain warm or warmer and at a temperature closer to the temperature of the indoor room, 20 degrees. So the addition of the external insulation reduces the heat flow and raises the temperature of the bricks so that there is no more condensation. The effect on summer of the addition of these 5 centimeters of external insulation is that first the temperature is inside, the temperature is quite flat. We don't have this raise. It's quite flat and at a bit higher temperature because there is also little losses to outside. But what is important is that if there is still some heat coming through the wall, we have now a phase shift of 12 hours. So the maximum indoor temperature is exactly 12 hours later than the maximum of outdoor temperature. And so the heat wave arrives into the space when we have very low outdoor temperature. We can ventilate with cool air and take away the heat. Let's see what we can do even better. Because still this, as you see, U value here is still described with a red bar, saying, you can do better. So if we have here 25 centimeters of insulation, then a number of things seems to be good. The U value is 0. Okay, let's say 27. So the U value is less than 0.15. Compare it to what it was 2, and now it's lower than 0.2. So we have reduced of a factor 10 the heat losses in winter. We have reduced by 90% the amount of energy which is which we lose towards outside. 90%. So imagine now all the problems we have, and we are trying to reduce energy expenditure and losses. With an external insulation, we can reduce 90% the winter energy requirements of a building. And another big important thing is that the interior surface, now it's at 19, so very close to 20, which is the temperature of the air. This increases the comfort indoor. Possiamo, aspetti che, ok, prego. Sì, esatto, l'ho mandata io. Però sto facendo una registrazione. Potete aspettare 3 minuti e ho finito. 3 minuti e ho finito. Sono con voi. So, this 27 centimeters of insulation outside are reducing by 90% the energy needs of the building, at least those that are due to the opaque part. Then we have the glazed parts and the ventilation. But let's say, at least from the point of view of, and those can be done very well also. From the point of view of the parts which are solid wall, we can reduce 90% what they lose in terms of energy in winter. Does it go well from the point of view of condensation? Yes, because the bricks are still even warmer, so there are even less risk that water vapor getting in contact with a cold material would condensate. There is no condensation, so the wall will stay safe, no damage to the wall. From the point of view of heat, okay, it's flat, so the heat wave, when it arrives inside, it doesn't raise the temperature of inside because the heat wave is blocked outside by this thick insulation. So even if there is the sun shining on the surface and hot air outside, this heat takes a lot of time to come inside. So, and in fact, we don't even have anymore the time shift. So there is nothing coming inside. So a very good winter performance, a very good summer performance, and a very good hygrometric performance. What we ask you to do at home, and then we discuss it next time, is, okay, your stratigraphy, how it is done. You can describe your stratigraphy here and calculate all these features for your case. And for a glass, we don't ask you to do the calculation because we have another tool to analyze glasses that we will see another time. But just to remember, we suggest you a good window, glazing plus good glazing, good frame, could have a U value of 1, 1.1. So the U value of a bad opaque wall is 2. The U value of a good opaque wall is less than 0.2. A glazing, the best glazing you can have, will be 1. So it will be much worse than a good opaque wall, much worse than this one. So a glazing will lose at least 5 times more than this wall, this opaque wall, well insulated. So you have to consider that even a very high performance glazing will, in winter, if you have a situation where you have cold air outside, will lose energy 5 times more than a good opaque wall. So the ratio of using opaque walls versus glazing should be taking into account this data. At least you know what you spend then to run the building, and you can choose, okay, which is the amount of glazing and amount of opaque that you want to use in your structure. So that's the idea, that you compare. At least you know, you have at least one part of the calculation available. And obviously for summer glazing, if not protected with sun shading outside, will let the sun energy enter immediately, not 12 hours later. So that's also a very big difference. Okay, up to you then to think in your case.